Congratulations, we have made it to the end of bonding. So we've gotten through Lewis structures, Vesper shape, polarity, and all that jazz, and we are wrapping up the bonding. Today when we talk about orbital hybridization and we talk about the different types of bonds that you can have, which are pi and sigma bonds. So we're going to go back for just a second to talk about the electron orbitals that you see when we talk about electron configuration. So scientists are pretty well able to map where you should be able to find an electron at any given point in time. And what I mean by that is 95% of the time you will find an electron hanging around in this area. And those areas were called the electron orbitals that we talked about. So S here, S orbitals, like 1s, 2s, that kind of thing, have a spherical shape, and 95% of the time you can find an electron within this sphere somewhere. The p orbitals have this dumbbell shape where we have like a dumbbell shape on the y-axis, the x-axis, and the z-axis. And then the d orbitals look like this. There's 5 different versions, and then the f's are even bigger than that, and there are 7 versions of that. And we've talked a little bit about how an electron pair that's shared between two things is what forms a bond. So when we talk about an actual bond forming, a bond forms when some of these overlap with each other. So we've talked about that overlapping of our electron shells. Well, that happens when, let's say, maybe something's S shell overlaps with something else's P shell. And we get our bonds. But if you look at the shapes of these, none of these match up with the actual Vesper shapes that we've talked about. And Vesper shapes are something that we can prove with a pretty fair amount of confidence that they exist and they have those shapes. And so it's one of those things where there is a mismatch between what we see in terms of the orbitals and what we see with the physical properties of the molecule. And so scientists had to kind of come up with a theory as to how we get these angles to show up. Because if I have a P shell overlapping with an S shell, I should get either a linear shape of 180 or I should get a right angle at 90 degrees. I don't see the shape of trigonal planar. I don't see tetrahedral. I don't see trigonal bipyramidal or octahedral. And so these shapes have to be explained some way. And the way that they try to explain them is through a process called hybridization. Now, it is a fairly complicated theory. We are going to be very surface level with this. I'm going to teach you kind of the bare bones of what you need to know for the test. And then if you want to get more into it, we can talk about it at, a Google Meet or in class at some point. But I'm going to show you the minimum that you need to know. And then if you want to know more, we can always chat about it later. Okay. So the theory is that these things called hybrid orbitals exist. And so again, the Vesper shapes that we know exist because these orbitals here, the S's and the P's, hybridize or merge together and form these new orbital shapes that give us the actual Vesper shapes that we're used to. So the first type of hybridization that we're going to talk about is something called SP hybridization. And SP hybridization happens in the molecules with 2 electron dense areas. So scientists try to explain the shape linear. If you think about 2 electron dense areas, we get the linear shape. They try to explain that by saying that when the 2 things bond together, an S shell and a P shell merge together, and out pops these 2 orbitals that look like this in red here. So they have kind of this node on them, and they have a smaller area and a larger area. And so the linear shape that we are traditionally used to seeing here is these 2 hybrid orbitals put together. The way that I keep track of what type of hybridization happens is by thinking about the electron dense areas and adding up the little numbers up on the letters for the hybridization. So if you think about this as 1s, so S1 and 1p, there are 2 orbitals that come together, and that's for 2 electron dense areas. Okay, So moving on then to 3 electron dense areas, that's going to be shapes that are trigonoplanar and bent with a bond angle of 120. This hybridization, what they think happens is an sp2 hybridization. So think about it as 1s and 2 p's hybridized to make 3 orbitals. So again, 1s, 2 p's, 3 electron dense areas. And what we end up getting here is the trigonoplanar shape that we are used to talking about. So the origin of the sp2 hybrid is that 2 p shell orbitals and an s shell merge together and they give us this shape. Okay, you need to be able to look at a Lewis structure and just tell me what the hybridization is. You don't need to tell me why it happens. And the last one that you're going to need to know is when you have 4 electron dense areas. That is called sp3 hybridization. So 1s and 3 p's merge together to give you 4 electron dense areas. The hybridization stands for the hybridization happening with tetrahedral, trigonal pyramidal, and the bent with a bond angle of less than 109.5. And it gives us that tetrahedral shape that we kind of talk about. Okay, so that's it for hybridization. There used to be some theories that trigonal bipyramidal happened with the merging of 3 p's, an s, and 1 d shell, but they don't really think that that happens. Most recent evidence suggests that that is not how that works. And so the College Board is only going to ask you guys questions about 2, 3, or 4 electron dense areas. And then 5 and 6 electron dense areas, they will not ask you the hybridization for. They sure as heck are going to ask you questions about the Vesper shapes and stuff like that, but not questions about the hybridization. But understand that the old theory used to be that the D shells kind of came into play with them. Okay, now there is another thing called sigma and pi bonding that we need to talk about, and this is a whole ball of wax. So I am just going to be talking about the very surface level stuff with sigma and pi bonding and what you need to know, but understand that this is literally like chapters on chapters in bonding classes. So if you want to talk about it, we can, but I'm going to save you that and just tell you exactly what you need to know. So a sigma bond happens when there is a direct overlap between 2 electron clouds. So I think we've talked about, you'll see me put my fingers together. It's when those 2 electron clouds directly overlap. I think about it as a handshake between 2 elements. So every bond that you look at when you draw it has one of these overlaps, these direct overlaps happening. So every bond has a sigma bond. Okay. So when you guys draw a line on a Lewis structure, that's a sigma bond. However, there is something called a pi bond. And a pi bond happens when there are p orbitals that didn't get hybridized into our Vesper shapes. And what happens is they can hold on to electrons and they can align correctly with a p orbital in another element, and then they end up making another bond. So what happens is pi bonding only happens when you have a double bond or a triple bond. And what happens is the first connection is the sigma bond, which is this green thing here. So that is the sigma bond, and that is the strongest. What happens is another bond forms with those p orbitals, and they're kind of attracted adjacently together. I think about it like a high five between elements. So it's a sigma shake and a pi high five. They kind of rhyme. If you think about the strength, a high five is not as strong of a connection as a handshake. So pi bonds are weaker than sigma bonds. And that's why when we talked about our bond energy, the double bonds did not have twice as much energy. It's because the pi bonds aren't as strong. So you say to yourself, this looks horrifically complicated. What do I need to be able to do? I got you covered here. So if you are looking at a molecule, they could ask you to tell you what the hybridization is around that atom, or what is the hybridization of this atom in this molecule. And you need to be able to identify how many electron dense areas there are and the hybridization. So if you have 2 electron dense areas, it's sp hybridization. 3 electron dense areas is sp2 and 4 is sp3. Like I said, count up how many orbits are involved, and that gives you your electron dense area. So for sp3, I have 1 and 3 gives me 4, so it's 4 electron dense areas. Okay, for the bonding, what they'll ask you to do is they will ask you to look at a Lewis structure and tell you how many sigma bonds there are and how many pi bonds there are. So when you draw a bond, every bond has a sigma bond. Not every bond has a pi bond. If you have a single bond drawn between something, it's 1 sigma bond and that's it. If you have a double bond, it is 1 sigma bond and 1 pi bond. And if you have a triple bond, it is 1 sigma bond and 2 pi bonds. So when we talk about these, this is all you need to know. These 2 tables, you need to be able to take care of that. So what I'm going to do is I'm going to actually go through some examples that are similar to your homework, and then we are going to kind of clear things up if you have any questions. So we're going to take a look at some Lewis structures for things. So the first thing I want you to do is I would like you to draw the Lewis structures for CO3 minus 2 and OCl2. So pause your video, get those Lewis structures drawn, and then we will go over them, okay? All right, so the Lewis structure for the carbonate ion, and I'm not going to go through how to draw them. If you are still struggling with Lewis structures, please talk to me so we can get things cleared up. But for time's sake, I'm going to draw these Lewis structures out just so we can crush out these examples. Okay, so here are my 2 Lewis structures. So on the homework, what I'm going to ask you to do is I'm going to ask you to draw the Lewis structure first, and then you're going to figure out the Vesper shape. So if I look at the Vesper shape for CO3 minus 2, I have 3 electron dense areas. Remember that this is 1 electron dense area, even though there's multiple bonds. So 3 electron dense areas and no unshared pairs. So my Vesper shape in this case is going to be trigonal planar. If I take a look at OCl2, I have 4 electron dense areas here. 2 of them are bonds and 2 of them are unshared pairs. So this is going to be a bent molecule. Okay, so these are all the kinds of questions that they could potentially ask you about these kinds of Lewis structures. Okay, the next thing is going to be polarity. So we've got to figure out the difference in electronegativity and then see if we have polar or nonpolar molecules. So if I look at the electronegativity for carbon to oxygen, this is a polar bond. Oxygen here has a partial negative charge. Carbon has a partial positive charge. Mine aren't as beautiful as the little delta symbols that you see, but we'll make it work. So because this has a trigonal planar shape and there are no dots on the central atom, that means that my carbonate is going to be non-polar. Now, there is a tricky little bit here because technically this has a charge here, but it is overall an ion, but these bonds here indicate that this would be a nonpolar part here. But again, because it's an ion, it actually makes it an ionic bond, but don't worry about that. So we'll just kind of test your logic here to begin with. This one here is a little more straightforward. So in the case of the OCl2, you have Cl to O, and I think if I'm doing this off the top of my head, the difference between them is 0.5. So there's not a huge difference, but there is a difference in electronegativity here. So the Cl has, I believe, an electronegativity of 3.0. O is 3.5. The difference is 0.5. So O is partially negative. Cls are partially positive in this case. Okay. The bent shape makes this polar because I have polar bonds and I have dots on my central atom, and that's going to make this a polar molecule. Okay. The bond angle for a trigonal planar is 120 degrees. Bond angle for this bent is less than 109.5. And that's because there's 4 electron dense areas. So that would make it tetrahedral shape, which is 109.5. Okay, those are things you've all done before. The last stuff is the hybridization and number and type of bonds. So for carbonate, the hybridization, I'm looking at the electron dense areas, and there are 3 of them. So the hybridization is going to be S, think about it, S1, P2. These have to add up to the number of electron dense areas. For OCl2, we have 1, 2, 3, 4 electron dense areas. So it's going to be S1, P3, or you could just write SP3, and that would be fine as well. Okay. Do not forget the unshared pairs. A lot of people do, and then you get them wrong. And the last thing then is the number and type of bonds. So if I'm looking here at carbonate, and I have my bonds here, each of these first lines that are drawn, that is a sigma bond. So I have 3 sigma bonds, which is drawn kind of like that. But you can also just write 3 sigma if you want. Okay, so there's 3 sigma bonds in this. And because I do have a double bond, I'm going to have 1 pi bond. So every first line drawn in is the sigma bond. Additional lines at that point are going to be pi bonds. And if we look here, we just have a line here and a line on the O. So that means we have 2 sigma bonds, and that's it. Okay, so you have a mega homework assignment that you should be working on. If you have any questions about that, please, please, please get some help with it. These are easy point questions that you need to be able to answer, especially hybridization and pi bonds, and basically all this stuff should be automatic. So if you are finding yourself having a hard time, please let me know and we will get things cleared up. Okay, if you have any questions, let me know. Good luck.